Good morning and welcome to this next lecture on sound and structural vibration. We are looking at transmission through a flexible panel, and we have reached this stage where you can see this is my power or intensity transmission coefficient because media on both sides are same. Okay, I just want to reiterate one thing here, that let's say the free wave number on the panel or free wavelength also is like this. Okay, we can only show the wavelength. Okay, and this is, let's say, the incidence axis. Now if, and this is phi, okay, this is phi. So if phi is becoming smaller, okay, phi is becoming smaller, what will happen is that the trace wavelength will become bigger. Okay, this trace wavelength will become bigger. Okay, so that the trace wave number will become smaller. Okay, so k sin phi will become smaller as phi reduces. I'm just giving the picture here. So this is the trace wavelength which is becoming bigger. So as wavelength becomes bigger, the corresponding trace wavelength wave number becomes smaller. Okay, so now that has to match your free wave number, and therefore the frequency angle is fixed. The frequency has to go up so that you can actually match the free wave number. Okay, we are talking so much because there are these terms where you have 1 minus the ratio of forced to free wave numbers. Okay, so in another way, if we want to see it again, if we have a free acoustic wave number line here, and this is my KB panel wave free wave number line over here. Okay, then let us say I have a certain angle at which I am incident. Then let's say this has to be the frequency for that angle, certain phi 1, such that I have a certain sin phi 1. So I have to be here at this frequency. Okay, for matching k sin phi 1 is equal to kb. If phi 1 is reduced, okay, then sin phi 1 is reduced, then I have to be at a higher frequency. I have to be at a higher frequency to match the free wave number. Okay, this is my free wave number line and this is my acoustic wave line. Okay, so now let's look at this picture which we have, or this expression that we have, tau p or tau is equal to twice rho 0 c sec phi divided by m omega whole squared. Okay, so by the same accord, okay, if I am at such a frequency that I am just barely at coincidence, okay, then phi 1 has to be 90 degrees. There is no other choice. And so if I am fall below this basic coincidence frequency, then I have no coincidence possible. Okay, so for a certain phi 1, I could be at a certain frequency higher than the basic coincidence frequency. Okay, this is my basic coincidence frequency here. Then I could be at some particular coincidence frequency that is related to phi 1, okay, such that k sine phi 1 is equal to kb. Okay, so when we mean low frequency, we will talk of low frequency. Okay, so we could mean that we are way below the basic coincidence, or we could say that we are way below omega c 0, the currently possible coincidence. Okay, so now my tau p is given by this, divided by twice rho 0 c by m omega sec phi plus k over kb whole to the power 4th eta sine 4 phi whole squared plus, let me write it here, plus 1 minus k by kb whole to the power 4th sine 4th phi squared. Okay, so now we are going to talk of low frequency, which means below the possible coincidence at a certain phi angle. Okay, so now what happens then? That means this term is small, this term is small. Okay, and if we say that the loss factor term is also small, then my tau is given by 1 over 1 plus omega m cos phi by twice rho 0 c whole squared. Okay, and based on materials placed in gases or metals placed in air and so forth, this term can be larger than 1. Okay, in which case the tau depends only on that term, so that my transmission loss or sound reduction index is 20 log to the base 10 again m omega cos phi by twice rho 0 c. Okay, you can see this is again the 6 dB increment per octave, or doubling of frequency. Okay, this is the mass law. Okay, now as I said, low frequency can be taken in two ways for a given phi. Okay, if you are above the basic coincidence, then there is a good enough range where we call low frequency. Okay, because at a certain phi the coincidence frequency is higher. Okay, now at coincidence, so at low frequency we are done. At coincidence, at omega c 0, okay, what happens? Now my k sine phi is equal to kb. So this term is actually exactly 0. Okay, now this term tau, after cancelling all the terms, can be written as 1 over 1 plus eta omega c 0 m cos phi by twice rho 0 c. Okay, whole squared. Okay, and therefore this region is now damping dominated. Damping dominated at coincidence. Okay, and this is the minimum value. This happens to be the or rather this happens to be the maximum value. This is the maximum value. Sorry, why the denominator becomes a minimum. So this is the maximum value. Okay. So maximum transmission value, that means transmission loss goes to a minimum. Okay. Finally, above coincidence, okay, the stiffness term dominates. Okay, so that what do we get now? We get tau given by 1 over 1 plus d k fourth sine fourth phi into cos phi divided by twice rho 0 c omega this whole squared. Okay, so this stiffness term can be bigger than 1. Okay, and therefore the transmission loss or sound reduction index becomes equal to 10 log to the base 10. Okay, d k fourth sine 4 phi cos phi by twice rho 0 c omega, and there's a square, so this becomes equal to 20. Okay, and then in k fourth we have omega to the power 4th, and below we have an omega here, so this is omega cube. Okay, so finally in terms of frequency we get 60 log to the base 10 of omega. Okay, so that means what, when frequency doubles, when omega becomes 2 omega, okay, we get 2 times log 2 times 60, which is 18 decibels. Okay, so in this range, for doubling of frequency, we get 18 dB increment in transmission loss. This is the stiffness control region. So what is the picture now? Okay, so the picture now is this here. So we have transmission loss. Okay, we have a transmission loss. Okay, so at a certain angle we have the mass law. Certain angle phi, we have a mass law. Okay, and let me pull this a little longer. Then you have a dip. This is coincidence. Okay, and you are at 18 dB per octave. Let me do this once here. So this is a certain angle. I get a dip and then I get 18 dB per octave. This is the stiffness control region. This is a smaller angle. Okay. Now what happens at a higher angle? Okay, at a higher angle I have because angle is small, coincidence occurs at highest frequency, right? Sine phi pulls it down, so frequency has to be higher. Okay, as my angle increases, okay, I have this line, I have this line, then I have a peak, I have a dip here, and then the dip starts to go parallel to again 18 dB per octave at the stiffness control region. So this is the coincidence at a higher frequency. Okay, and it continues. So now if I take a further higher angle, then I'll have a dip here, and then the dip will continue at 18 dB. Okay, smaller angle, higher coincidence, higher angle, lower coincidence. Okay, so this is increment in phi. This is 6 dB per octave. They don't look very different, sorry. Okay, this is 18 dB per octave, this is 6 dB per octave. Okay, and finally if you actually do normal incidence, okay, normal incidence, then phi is 0, then tau is going to be twice rho 0 c whole squared by twice rho 0 c whole squared plus m omega whole squared. Okay, and so if, which typically m is a bigger entity, mass dominated, then we'll have transmission loss given by 20 log to the base 10 m omega by twice rho 0 c, which will be some curve here which is parallel to the 6 dB curve but keeps going, parallel to the 6 dB curve but it keeps going. This is phi equal to 0, normal. Okay, so there are many more studies that can be done in transmission. Actually, when you have a building, okay, when you have a building and there's a window and there is traffic going by and there is sound reaching your window, okay, so there's going to be a transmission of sound into your room. Okay, then you have double walled windows, okay, 2 layers of windows that are used. So now that could be a study on how to layer, could have 2 layers, so 2 flexible partitions, and the sound wave is incident. So what is the sound wave transmitted? So there are such studies possible, and also averaging across angles, what is a angularly averaged transmission, but those are at this stage beyond this course, so I will not get into that. So I think to give a basic idea of sound transmission, this is a good enough section. The next important topic is sound and structure interaction. in cylindrical geometries. So, cylindrical objects like pipes, okay, carrying fluid, are quite common, and of course we have aircraft which are approximately cylindrical, and there is a noise problem associated with aircraft. Okay. So, we will look at how cylindrical shell vibrations couple with the fluid inside, okay, or the fluid outside, and we look at it for this course in infinite geometries. So, this is a cylindrical shell which is flexible, okay, it can vibrate, carry waves, and it extends to infinity in this direction. Most likely that will be my x direction, okay, and this will be theta direction, and then that is radial. Now, one more thing we will mostly talk about coupling of shell vibrations with internal fluid. Okay, not so much with exterior. Is a very elaborate topic. More or less you can spend a lifetime in it, and so it's just a taste of what it is. This could become actually a separate topic entirely for a course, so we'll just skim through some details. Okay. So, firstly we'll just look at cylindrical shell vibrations and waves in an infinite cylindrical shell. So, if I draw a shell element, it looks like this. Let us say I place my coordinate here, this is my x axis, and let us say this is my theta direction. Okay. Now, I will just put my force or stress resultants So if that is the x direction, I'll have this will be nxx, this will be nxx plus an increment. I will not write the increment all the time. Increment will be of the form del n xx over del x dx, of this form. Okay, there's no space, that's why. Then we'll have n on the theta face in the x direction, n theta x plus delta. Okay, then we have let's see, n theta theta, and this will be n theta theta plus increment. Okay, then we'll have vertical shears resultant qx3 plus delta, then q theta 3 and q theta 3 plus delta. Okay, then we have, let me, n x theta and n x theta plus delta. These are the stress resultants. Now in terms of this stress resultant, we can write the shell equations for a harmonic response. Which will look like del n xx over del x plus 1 over a del n theta x over del theta plus rho h omega square, or let me say rho s omega square u x comma theta equal to 0, then del n x theta by del x plus 1 over a del n theta theta by del theta plus q theta 3 over a plus rho sh omega square v of x comma theta equal to 0, and del qx3 by del x plus 1 over a del q theta 3 by del theta minus n theta theta over a omega square w x comma theta equal to 0. So u x comma theta is axial displacement. Okay, axial displacement of a point, okay, in the x direction, axial displacement. Then v of x theta is torsional. Okay, it's this way. V displacement is this way. Then W displacement is transverse. Okay, this is in the x direction, this is the theta direction. We can make this in the z direction. Okay, and we are looking at thin shell theory. Thin shells. Okay, where the thickness of the shell to the radius of curvature is in some thumb rule, okay, less than 1/20. And so that the displacements are described in terms of the shell mid surface and slopes. Okay. So there are these approximations. So if these approximations of displacements are described, okay, u x comma theta, v x comma theta, w x comma theta, okay, and then from there you compute your strains linear, okay, and then you compute your stresses, and then from the stresses you come to stress resultants. Which means we can put the stress resultants in terms of mid-plane displacements. Okay, mid-plane displacement. Then what happens is you have the entire 3 equations. Okay, so I didn't say it, I suppose. So this describes the axial motion of the shell element. This describes the theta direction or torsional, okay, force balance in the torsional direction. This is force balance in the transverse direction. Okay, so this is dx, this distance is dx, and this angle is d theta. This angle is d theta. So if we put back the displacements into these 3 equations, put the stress resultants in terms of displacements, and how do we do that? We further describe them as cos n theta e to the power of minus I k n s x e to the power of I pi by 2 v of x comma theta is equal to v tilde ns sin n theta e to the power of minus I k n s x, and w of x comma theta w tilde ns cos n theta e to the power of minus I k n s x. Okay, these are the mid-plane displacements. After this, if this is substituted back into the equations that are in terms of displacement derived from stress resultants, then what we get is a matrix. We get a matrix, okay, which has L11, L12, L13, L21, L22, L23, L31, L32, L33 equal to 0. We are running out of time, so I will close the lecture here and continue next class. Thank you.